Hello everyone and welcome to the coronavirus edition of the 10th exercise from our signal theory class. In this exercise I will show you some examples of block diagrams and then we will play with the state space representation. Here I have a difference equation of a second order system and I want to draw its block diagram in the direct form too and in the transposed form, and I want to do it both in time domain and z domain. To do this, I need to be able to derive and then remember what the structures of the individual types of block diagrams are. When I know what the general structure is, I just need to identify these A and B coefficients and substitute them into the block diagram. So in this case, my A0 is 7, so at this place I'm supposed to have 1 over A0, so here I will have 1 over 7. My A1 is 2, here I'm supposed to have minus A1, so here I will have minus 2. This 3 will come here with negative sign, this 4 will come here, this 5 will come here, this 6 will come here. And this is the direct form 2 block diagram in the time domain. When I want to do it in the z domain, I get pretty much the same structure, except instead of the time domain signals, I will have there z images, and instead of these time delays, I will have multiplication by z to the minus 1. The transposed form looks like this. Again, it stems from the generic structure from the transposed form, and basically these constants will come here and these constants will come here. Again, this is the equivalent in the z domain. I suggest that you try to do this yourself and then you compare your results with what you see here. And you should be able to do this in the opposite direction as well. When I give you the block diagram, you should be able to identify what are the A and B coefficients, and using those coefficients, you should be able to write the difference equation. So practice that a little bit as well. On this slide, I have a variation where I want to draw the same schematics as on the previous slide, but this time I want to do it based on the transfer function. This is quite similar to what we had in the previous slide, except this time I need to be able to identify what are the A and B coefficients from the transfer function. So if I take this time domain direct transposed form as an example, I need to take a look at the B coefficients and write them here. So this number 1 will come here, this number 2 will come here, this number 3 will come here, and I need to write 1 over A0 here, so 1 over 4 will come here, and I need to write negative coefficients A here. So this will come here as minus 5 and this will come here as minus 6. The other forms are done in similar fashion, so try them yourself and compare your results with what you see here. And you should be able to do this in the opposite direction as well. If I give you a block diagram like this one, you should be able to identify what are the A and B coefficients, and using those coefficients write the transfer function. So practice that a little bit as well. On this slide, I have examples of block diagrams for a continuous time system. A continuous time system can be described using a differential equation or a transfer function. To draw the block diagrams, you again need to be able to derive and then remember what are the structures for the individual types of block diagrams. When you know what the generic form of a block diagram is, you just need to identify these A and B coefficients, either from the differential equation or from the transfer function, and then you just need to substitute into the generic form of the block diagram. So if I take the controllable form in the Laplace domain as an example, this is how I draw its schematic. At this place I should have 1 over A2, my A2 is 7, my A2 is 7, so here I will write 1 over 7. At this place I should have minus A1, my A1 is 2, my A1 is 2, so here I will write minus 2. This number 3 will come here as minus 3, and this 4 will come here, this 5, which by the way in the transfer function is this 5, will come here, and this 6, which in the transfer function is this 6, will come here. So this is your controllable form in the Laplace domain. There is one detail you should be careful about. With the continuous time systems, the indices of the coefficients rise from bottom to top. We have b0, b1, b2, minus a 0, minus a 1, 1 over a2. With the discrete time systems, the direction was opposite. With the discrete time systems, we had b0, b1, b2, 1 over a 0, minus a 1, minus a 2. So be aware of this detail and do not mess it up. So go ahead, take this difference equation or this transfer function and draw one of these forms of the block diagrams. And then do it in the opposite direction. Take another form of the block diagram and try to write the difference equation or the transfer function. On previous slides, I always illustrated block diagrams on second order systems. Block diagrams for higher order systems are a simple extrapolation. But just to make sure that you are able to do it, here I have two examples of fourth order system, one in discrete time and one in continuous time. This is the difference equation of the fourth order system in discrete time. This is the transfer function of the system. Here you have it written in negative powers of z, and here you have it written in positive powers of z. This is the block diagram in the transposed form. This is the coefficient b0, which comes from here, here, here. This is the coefficient b1, which comes from here, here, and here. This is the coefficient b2, which comes from here, here, here. This is the coefficient b3, which comes from here, here, here. And this is the coefficient b4, which comes from here, here, and here. This is 1 over a 0. That is 1 over this number. This is minus a 1, which comes from here, here, and here. This is minus a 2, that comes from here, here, or here. And this is minus a 3, which comes from here, here, or here. And this is minus a 4, which comes from here, here, or here. Now the continuous time system. This is the differential equation, and this is the respective transfer function. This is the block diagram in the direct form in the time domain. Now, this is the coefficient b0, which comes from here or here. This is the coefficient b1, which comes from here or here. This is the coefficient b2, which comes from here or here. This is the coefficient b3, which comes from here or here, and this is the coefficient b4, which would come from here or here. This is minus a 0, which comes from here or here. This is minus a 1, which comes from here or here. This is minus a 2, which comes from here or here. This is minus a 3, which comes from here or here. And this is 1 over a 4, which comes from here or here. So this is how you draw the schematics for higher order systems. And you should be able to do this in reverse. When I give you the schematic, you should be able to identify the coefficients, write the transfer function or the differential equation. Let's take a look at the state space representation. This is a simple state space representation, and I want to draw its schematic and write it in the matrix form. When I want to draw the schematic, I will start with expressing the relationship between the derivative of the state variables and the state variables themselves. When I take derivative of the first state variable and I integrate it, I will get the first state variable itself. When I take derivative of the second state variable and I integrate it, I will get the second state variable itself. So this is how I get this core part of the block diagram, and I will finish the rest using these equations. So the derivative of the first state variable is equal to 2 times x1 of t, 2 times x1 of t, plus 3 times x2 of t, plus 3 times x2 of t, plus 4 times u of t plus 4 times u of t. And that will give me the derivative of my first state variable. Now the derivative of the second state variable, that is equal to minus 5 times x1 of t. Here I have it, minus 5 times x1 of t plus minus 6 times x2 of t plus minus 6 times x2 of t plus minus 7 times u of t minus 7 times u of t. Now the output, the y of t, that is equal to 8 times x1 of t. The output is equal to 8 times x1 of t plus 9 times x2 of t plus 9 times x2 of t plus minus 1 times u of t minus 1 times u of t. So this is the schematic, the block diagram of this state space representation. Here I have written the state space representation in the matrix form. That is very simple. These constants will create your state matrix A. These constants will create your input matrix B. These constants will create your output matrix C, and this multiplication by minus 1 will give you the feed-through matrix D. Here I have another example with the state space representation. This is now my state space representation, and I want to find the input-output representation. Because this is the simple case where the output is equal to one of the state variables, I can do this very simply in the time domain. I need to take this output equation and substitute it into these two state equations. When I do that, I will get this. In these equations, I have the output, the input, and the second state variable. To turn this into the input-output representation, I need to eliminate this second state variable. To do that, I need to take the state equation where this second state variable is not in the derivative, that is this first state equation, and from this first state equation, I need to express the second state variable, which is equal to this. Now I need to take this and substitute it into this equation. When I do that, I will get this. Now I need to crunch, and when I simplify everything, I will get this equation, which is the input-output representation corresponding to this state space representation. On this slide, I have yet another state space representation. This time the output is function of both state variables and the input of the system. And I want to draw the schematic, write this state space representation in the matrix form, write the transfer function of this system, and find the input-output representation of this system. Let's start with the schematic. When I draw the schematic, I will start by drawing the relationship between the derivative of the state variables and the state variables themselves. So this is the derivative of the first state variable. When I integrate it, I will get the first state variable itself. This is the derivative of the second state variable. When I integrate it, I get the second state variable itself. The rest will come from these equations. The derivative of x1 is 3 times x1 plus 6 times x2 minus u. The derivative of x1 is 3 times x1 plus 6 times x2 minus u. The derivative of x2 is minus 3 times x1 minus 5 times x2 plus u. The derivative of x2 is minus 3 times x1 plus minus 5 times x2 plus u. The output is minus 8 times x1 minus 12 times x2 plus 3 times u. The output is minus 8 times x1 plus minus 12 times x2 plus 3 times the input. So this is your schematic, your block diagram. Now the matrix form. That is again very easy. These numbers will give you your state matrix A. These numbers, this minus 1 and plus 1, will give you your input matrix B. these numbers will give you your output matrix C, and this number will give you your feed-through matrix D. So this is the state space representation in the matrix form, which will become handy when I will try to find the transfer function. On the lecture, I showed you that the transfer function can be expressed using these matrices A, B, C, and D in this form. So when I want to find the transfer function from the state space representation, I need to evaluate this expression, which is a little bit ugly but certainly doable. So here I have substituted for these matrices. This is my matrix C, this is my matrix A, this matrix, this is my matrix B, this matrix, and this is my matrix D. Now the ugliest part of this is the computation of this matrix inverse. I will start by writing down what is the expression within this bracket equal to. So here I have S times the unit matrix minus this matrix. That is equal to this. Now on the next line I will just copy this matrix, I will copy this matrix, and I will just copy this matrix. And I will express the inverse of this matrix. The inverse of this matrix will be given as 1 over the determinant of this matrix. This is the determinant of this matrix, and that you can compute as this term times this term minus this term times this term, and that is what you have here. Also, the inverse of this matrix will contain this matrix of cofactors. For this position, the cofactor is this term, this s plus 5. For this position, the cofactor is this term, this s minus 3. For this position, the cofactor is negative this term, which is this plus 6, and for this position the cofactor is negative this term, which is this minus 3. So this is the inverse of this matrix. Now this is just a scalar, so I can pull it in front of this matrix multiplication, and when I simplify this a little bit, it will give me this. The rest of this expression was created by copying this matrix here, taking transpose of this matrix here, and by copying the rest here. Now I just need to evaluate this matrix multiplication. So first I will multiply this matrix by this matrix, which will give me this, and this can be simplified into this. And now I will multiply this matrix by this matrix, and that will give me this. And this I can simplify to this. This I can put to the common denominator, which will give me this. That I can simplify, and I will get this. And this is the transfer function of the system described by this state space representation. And from this transfer function I can find the input-output representation. These are the coefficients B0, B1, B2, A0, A1, A2. Using those coefficients I can write this input-output representation. Moreover, this example nicely demonstrates that you can compute the poles of this transfer function using the state matrix as the values of S for which the determinant of this matrix is equal to 0. Why is that? The poles of the transfer function are the values of S for which this denominator is equal to 0. Now, this denominator was created from this expression, which was the determinant of this matrix, which is this matrix. So when you know the state matrix, you can compute this determinant, which will give you this, which is equivalent to the denominator of the transfer function. You can set it equal to 0, and the values of S for which this is equal to 0 will give you the poles of the transfer function. So in this case, the system seems to be stable because the poles of the transfer function have negative real part, and the system seems to be underdamped because those poles are complex. On this slide, I have an example where I want to do the transformation in the opposite direction. Here I have the input-output representation of the system, and I would like to find the state space representation. To do this, I will denote the output of the system as the first state variable, and I will denote the derivative of the output as the second state variable. Now when I substitute this equation into this one, I will get this, and I will use this as my first state equation. To get the second state equation, I will get these two equations and I will substitute them into this input-output relationship. This equation will come here, and this equation will come here and here. When I do the substitution, I will get this. Now from this equation, I will express the derivative of the second state variable, which will give me this. And now, this will be my first state equation, this will be my second state equation, and this substitution I will use as the output equation. When I put it all together, I will get these equations. Here I have moved these variables so that it is easier for me to see the constants that will come to this matrix form of the state space representation. And this is how you can turn this simple input-output representation into this state space representation.